Good afternoon, everyone. Welcome to my talk, Immoral Fiber, Unlocking and Discovering the Offensive Capabilities of Fibers. Now, first, a little bit about me. My name's Daniel Jerry. I'm a security researcher. Previously, I was a senior security researcher for WithSecure and F-Secure in their strategic endpoint research team. Prior to that, I worked for UK Intelligence in a similar role and an agent developer for about 5 years. And I've also worked as an R consultant for Mandiant. So what are we going to cover today? Well, first off, what are fibers? I'm going to give you a little brief overview so you understand the core components. Then we're going to talk about the existing threat landscape and some open source techniques already available. And then following this, we're going to dig into 2 new offensive techniques that I've developed, and finally round off with some conclusions and key takeaways. So first off, what are fibers? Well, fibers are just another vehicle to execute code. Think of them as mini threads. Microsoft's definition is on the slide right now, but I prefer to define them as stackful coroutines. Now, these are just like functions that have stacks, except they don't return like a regular function. They're manually switched to by the application itself, and they're a user mode concept invisible to the kernel, and only one thread can run one fiber at any one time. Now, they're initially designed when CPUs had less cores and threads available to them, and they were used in things like SQL database servers. These days, Microsoft actually recommends not to use fibers where possible, but people still do in sort of things like browsers and audio software plugins. So what are the components of a fiber? Well, first we have our fiber object, and this contains our fiber data and context structure. Then we have fiber local storage. Now, this is the functional equivalent to thread local storage, and it allows a fiber to store and retrieve values unique to each fiber based on an index. And then finally, these are tied to callback functions. And these are functions which are executed whenever one of the indexes is freed or the fiber object itself is deleted. Some basic rules about using a fiber. To first use a fiber, you need to convert your thread to a fiber. There's no main fiber. Every fiber is considered equal, so it's very egalitarian. Any fiber is free to create or delete another fiber, but crucially, only one fiber can run per thread at any one time. And they're controlled by this simple API. And the main reason for this simplicity is that we don't have any synchronization objects to deal with. And by that, I mean mutexes, semaphores, waitable timers that you do with threads. And that's because they're inherently synchronized by the application itself using the switch to fiber function. So how would one use fibers with Fiber API on Windows? Well, first we need to convert our thread to a fiber with convert thread to fiber. Then we create a new fiber with create fiber. Optionally, at this point, we could allocate some fiber local storage unique to that fiber. And then when we're ready to execute this newly created fiber, we call the switch to fiber function. When we finish, we can either convert our fiber back to a thread with convert fiber to thread, or we can delete the fiber or delete the overall thread itself. So if you're interested in more of a breakdown of what fibers are and the internals of fibers, then I recommend you check out my talk I did last year from a defensive perspective, and the QR code is on the screen. But this talk's more interested in the offensive techniques and capabilities of fibers. So why fibers from a defensive perspective, or an attacking perspective even? Well, they're actually a delivery mechanism. They're not a UAC bypass, they're not a privesc. What they are is another alternate execution method beyond just using a straight-up fiber. And that means the heuristics that you might use from a detection standpoint for threads don't always apply. They're also old, and that's not necessarily a bad thing. In fact, it's actually a positive thing, because we can rely on them being there as an option in order to execute our payload. And although Microsoft's advice is not to use fibers where possible, if you interrogate some of the system processes, Microsoft actually makes use of fibers themselves. And why do they appeal specifically to attackers? Well, simplicity. There's a very low barrier to entry. You've seen how basic the API is. I've managed to talk you through it in a few seconds. And on top of that, they're slightly obscure and niche, so they're not as likely to be taught in like defensive 101 classes. Getting at dormant fibers, i.e. fibers that aren't currently executing, is actually non-trivial because there's no sort of set functions to use. And then fundamentally, this moves into an immature detection capability. So a lot of EDR products will use kernel callbacks, say like thread notification, creation and deletion events. But because a fiber is a user mode concept, a fiber is born and dies in between those two events. Therefore, we don't collect any telemetry. On top of that, the call stacks are different. So we have to write a whole new set of signatures. There's no remote enumeration functions in the Windows API like there is with threads. And there's also limited open source tooling available as a result of that. And there's no ETW specific providers, which a lot of EDR agents use, that target fibers specifically. And you might be wondering, are fibers actually being used? Well, a quick Google search shows numerous POCs on GitHub that are all kind of AV evasion based that make use of fibers. And a handful of blog posts too, saying, look, if I use fibers instead of a straight up thread as my delivery mechanism, it lowers my AV detection rates. So what's the first technique? Well, this is the overwhelming majority of those POCs use this. And it's basically just to execute your shellcode directly using a fiber. So like before, we convert our thread to a fiber. Then we allocate some memory and store our shellcode to it. We can do this in any number of means, but I've just put one example on the slide. Then we create our new fiber and supply a pointer to our shellcode. And then when we're ready, we call switch to fiber to switch the execution, and our fiber's shellcode is executed. Simples. So what are the advantages of using this? Well, we don't create any new threads. So we avoid kernel callbacks for thread generation events. We also avoid using thread-specific APIs that might be targeted by detection tools. It's really, really simple to implement, and the remote fiber enumeration is particularly tricky. The disadvantages, well, we still need to allocate space for our shellcode to store, and there's actually an artifact inside the thread information block, which is inside the thread environment block, a standard Windows data structure, known as a fiber data pointer. So that could be potentially used as an artifact. And on top of that, fibers in general are less common than threads, so there's less space to hide. The second technique is to use fiber local storage callbacks and define a malicious callback. So like before, we convert our thread to a fiber. This time, we allocate some fiber local storage, and we supply a pointer to our evil callback. Then, optionally, we can supply a parameter to this callback that we've defined earlier. And then we're ready to execute it. We either delete the fiber, exit the thread, or free that fiber local storage index, and this triggers the execution of the callback. On older versions of Windows, you also had a pointer to the callback table in the process environment block, so you could overwrite existing callbacks with your malicious callback. Now, what are the advantages? Well, the callback table is hidden on newer OS builds, and the structure is undocumented, so that's good in an attacker's perspective. There's no artifacts in the standard Windows structure, such as the thread environment block or the thread information block. The payload could also be chunked up over multiple different callbacks, so you could chain your exploit together and separate that exploit code out if you so desire. And the implementation is actually very trivial. The disadvantages, if you're overwriting existing callbacks, you need to be careful so you don't introduce instability into the application itself. And we still need to allocate some memory in order to define our malicious callback. And then finally, the last open source technique is call stack masking. So when running a thread and a fiber inside that thread, you'll only present the stack of the currently running fiber. So when you're not executing malicious code, say when your beacon or your payload is sleeping, then you can switch to an innocent-looking fiber with an innocent call stack, thereby masking it. And this technique was actually implemented in Cobalt Strike a couple of years ago and has subsequently been picked up by some open source POCs too. So why callstacks? Well, EDRs would traditionally collect data via Usermode hooks on sensitive functions that are abused by malware. So in this instance, we have ZW create file. Then they record the parameters that have been provided to them and see which process is actually accessing them. So attackers realized this, and they started using direct syscalls, whereby you jump directly into the kernel and skip this hook. But as you can see, if we collect callstacks, then we can clearly see this from a defensive aspect, especially if that call into the kernel has come from some unbacked region of memory that our shellcode resides in. And you can basically collect callstacks in three main ways. You can do periodic scanning, so taking a snapshot of all the currently running threads and unwinding the stacks. You can be more targeted, so you only wanted to target threads that are in a wait state, i.e. your sleeping beacons. Or you can do inline of event-based callstack collection. So you'd have like a pre-existing hook or kernel callback that records callstacks when a certain event on the operating system is triggered. So how does it actually work? Well, we have Fiber 1 with our malicious callstack. We have Fiber 2 with our clean, innocent callstack. Fiber 1 calls switch to fiber when it wants to rest, i.e. our payload wants to sleep. And this switches the two fibers, so the innocent fiber is now swapped into the context of the running thread, and this is where we sleep. When a memory scanner comes along, does like a periodic scan, it reports, hey, we're clean, no worries. And the advantages of doing this is basically it protects against periodic and targeted scanning, and on top of that, it maintains legitimate stacks. So a lot of stack spoofing techniques will modify the call stacks with gadgets, and then you can detect that based on like heuristics to check to see if their stacks are valid or not. It doesn't apply here because the stacks remain valid throughout. Also, it's a lot more trivial to implement than traditional call stack spoofing techniques. And we're not using any APCs or sacrificial threads or suspending any threads to do this. And on top of that is a user mode concept. So we're not going to generate any kernel callback events for it. The disadvantages, though, is that we could target fiber-specific indicators. So there's a couple of indicators, the same TED flags field, which is inside the thread environment block. And we could also look for the start routine of fibers in the call stack. It also doesn't protect us against inline event-based call stack collection, depending on what our payload is doing, if it triggers those. And if we can design a tool that enumerates dormant fibers, i.e. those that aren't currently running, then we can scan them and reveal the mask. So one of those indicators, the fiber start routine, was actually highlighted in a MDSec blog post as to how to potentially look for sleeping beacons from Cobalt Strike. And last year, I wrote a tool called Weetabix when I dug into this topic that looks to extract all of that fiber telemetry from memory, including the dormant fibers, and was able to detect all these techniques. I know of at least one EDR solution that's now currently using this, and imagine a few more have their own techniques built in. But having dug into the internals of fibers, I realized, can we take this further? Can we expand on these techniques, make them a little bit more sophisticated? And crucially, can we open up the use case as well? So with that in mind, I kind of built some next generation tooling. So the first tool I built was Phantom Thread. Now, this is an evolved method of call stack masking that looks to address some of the weaknesses from the original technique. By that, it removes the ability of memory scanners to target fibers specifically. And in addition, it also masks the dormant fiber as well as the currently executing fiber. So to avoid being targeted, we could masquerade as a thread. And to do that, we look at that same TED flags field from earlier. This is the OS's way of distinguishing fibers from threads. And it does that by flipping the 4th bit inside the convert thread to fiber API call. And this check is actually performed in the following fiber APIs. So knowing this, what we can do, we can temporarily patch that to that of a thread. And then anytime we wish to call those fiber APIs in our payload, we can temporarily switch it back. Next, we want to remove that fiber-specific start routine from the stack. And basically, that was what was highlighted in MTSEC's blog post. But if you have a look, this is only present in fibers that have been created from the initial fiber. So if we perform our sleep during our payload in the initial fiber created from the thread, then we maintain the thread start routine, thereby avoiding leaving the fiber start routine present in the stack. And then finally, if we look to mask our dormant fiber in addition to our currently executing fibers, because tools such as Weetabix enumerate dormant fibers as well, therefore revealing the mask. So to do this, we first create a dummy fiber using either a template or copying the existing running fiber. Then we patch the dummy fiber in place of the malicious fiber when it's sleeping. Then when it scans, it reports, hey, both the running fibers and the dormant fibers are clean. After this, we could either delete our malicious fiber, and that's only if we want to run it maybe a handful of times, or we can restore it and switch the execution back to it and then repeat the masking process again. So when switching to a dummy fiber, if we want to switch to this permanently, we need to also pass a sanity check, and that's based on this value known as the XORed cookie value. And basically, to do this, we transplant that cookie and we regenerate it, and we copy it into our dummy fiber object. So when we put this all together, we get a fiber that has the same TEB flags field to that of a thread. We have no fiber start routines in our call stack, and the malicious fiber object is masked in addition to the currently running fiber. And the advantages of using this? Well, we don't have any fiber artifacts, so we can't be targeted specifically by a memory scanner. We have valid call stacks, like before. In addition, we also have the dormant fiber masked, and we also haven't created any sacrificial threads. The disadvantage is that we still don't protect ourselves against real-time call stack collection if our payload is going to be triggering that. The next up is dormant fiber, poison fiber. So every other technique I've spoken about thus far has been local to a process that you control. What poison fiber does is it remotely targets processes that are making use of fibers and then injects into them. And it does this by either injecting directly into a remote dormant fiber or by introducing a new malicious callback. Then it relies on the application that we've injected into to schedule our shellcode for us. So here we're going to cover how to remotely enumerate fibers, then how to inject code directly into the dormant fibers, and then following that, how to inject malicious callbacks. So how do we remotely enumerate fibers? Well, first we identify threads using fibers, using that same TEB flag field from earlier. So we take a snapshot of all the currently running threads, and we interrogate that field. We see if that fourth bit is set. If it's set, we can say, hey, this is currently running a fiber. To pick out the dormant fibers, we want to look inside the APIs that create fiber objects, and we can see that there's consistency. They always use a requested block size, a heap block size of 530 hexadecimal bytes. So we take that, and then we remotely enumerate each heap block entry in a target process. And then we do that using the following steps. If you're more interested in the breakdown of that, I put a QR code on the screen which takes you to the video where I explain this a little bit further. But essentially what we do is we look at the PEB remotely, then we find the number of heaps, then we enumerate the heap segments, and then from there we get each heap block, and we look at the actual size and the unused bytes to generate the requested size. And with that, we generate a list of potential fiber objects. But that's not enough. We can't just say based on this allocated size. It could be anything else, right? So we need to validate these fiber objects. And within each fiber object, you get this XORed stack cookie that I mentioned earlier. And this is made up of 3 fields, fiber data, which is also inside the fiber object, as well as the stack base. And then we have this third value known as the base P fiber cookie. Now, this is a randomly generated value that's created upon thread creation. And what we can do is we can basically rearrange that equation that's used to generate the XOR cookie to figure out this base P fiber value, because this is the only value that we don't have. And once we know this value, we can take the list of those heap objects and we can compute an expected fiber data value from these heap objects. Now, if the expected fiber data value matches that of the actual fiber data value, we can concur that this heap object does indeed contain a dormant fiber. So now as an attacker, we've gone through those steps. We have the currently running fibers and the dormant fibers. So let's start by injecting into those dormant fibers. So a fiber object contains a context, and this records the saved execution state of a dormant fiber. And inside this context is an instruction pointer. And what this does, it points to a ret, which has the side effect of taking what's ever off the top of the stack in that dormant fiber and then jumping to it, therefore resuming code execution. So knowing this location, we can overwrite that, providing there's enough space, with our shellcode. And then whenever this dormant fiber is switched to, it will execute our shellcode instead of the original dormant fiber code. Another method is via redirection. So instead of overwriting that dormant fiber code, we can allocate a new region of memory remotely and then push the address of this on top of that dormant fiber stack. That way, when a fiber is switched to, it will execute our new region of memory first, and then providing our shellcode ends with a ret, it will return execution back to the legitimate fiber code and continually run the application as usual. So the advantages of this, well, we can now target processes using fibers and inject into them remotely, which we couldn't do before. There's also no need for us to trigger the execution because we just rely on the inherent switching of that application that we've injected into. We're also not creating any new threads. And then when we're overwriting fiber code, we're actually not, providing there's enough space, allocating remotely any new regions of memory. We're just changing the permissions on that memory region. Now, the disadvantage is, if we are looking at all threads across a system and we're taking a snapshot, then that's potentially quite noisy. So we need to bear that in mind. Also, there's race conditions possible between the time which we inject our malicious fiber code and the time at which the application switches to that dormant fiber. And on top of that, if we're overwriting existing fiber code and we're not cleaning it up afterwards, then as soon as our shellcode finishes executing, we'll introduce some sort of crash or exception handling. And when we're redirecting, we still are remotely allocating memory, so we need to watch out for that too. The next method is remote callback injection. So first we need to collect the callback table of the remote process that's using fibers. And we do this through the FLS data pointer that we found in our dormant fibers. And what this does, it points to an entry in a W-linked list. And one of these entries doesn't actually represent a fiber object. Instead, it represents a global fiber local storage struct. And inside this struct is a pointer to the callback table. And the first field of this callback table defines the number of callbacks present. And then the subsequent fields will be either hard-coded values or values to pointers to fibers. Sorry, pointers to fiber callbacks. So what we can do, we can either overwrite an existing callback with the address of our malicious callback, or we could increase the size of this callback table and then append a new callback to the end of it. And then whenever the associated index is freed, the fiber is deleted or the thread itself exits, what happens is there's a couple of functions inside NTDLL which scan the callback table and then execute our malicious shellcode inside the callback. And the advantages of this, well, our injected callback is actually cleaned up remotely by the application itself for us, so we don't have to bother with cleanup. And if we're appending callbacks, then we're not overwriting any critical fiber local storage callbacks that may have been defined by the developer. The disadvantages, though, is we need to know that fiber local storage is already present in that remote application, which in most cases you'd assume it was, but we can still check for this. On top of that, it's a one-time execution method only because the application, as soon as it's triggered the callback, will clean it up. And if we are overwriting callbacks, we need to be careful which callbacks we overwrite so we don't introduce instability or crashes. And finally, some conclusions and key takeaways. So can we go further with these techniques? I think we can a little bit. So for phantom thread, we're not protected against inline callstack collection. So packaging it with, say, like another technique, such as DLL proxy loads and Windows callbacks to make our stacks look a little bit more legitimate might be a good idea. And on top of that, we could also encrypt that dormant fiber object that we've temporarily patched out for our dummy fiber in case it gets scanned by like overall generic memory scanners. For poison fiber, I think improvement-wise is to provide some built-in cleanup capability, so we're not introducing crashes if we're just overwriting directly that fiber code. And by that, I mean perhaps use something like a vectored exception handler that captures the crash and replaces it afterwards and resumes execution. And finally, some key takeaways. Well, fibers can be used as an alternate execution and delivery mechanism for your payload. And you can use this to sidestep, say, some traditional telemetry sources and heuristics that are more inclined to target threads in the clean manner. 2, well, remote fiber injection is now possible thanks to poison fiber, and that expands its use case to attackers. And then 3, to prevent evasion techniques becoming, in amongst themselves, high-fidelity indicators, it's important to remove the artifacts where possible. And by that, I mean we've removed those same tip flags and RTL user fiber start within phantom thread. So thanks very much for listening to my talk. The QR codes for the tool repos, Weetabix, the defensive tool, is on the slide. I'll be releasing Immoral fiber over the next couple of days. Does anyone have any questions? I guess you could have a callback that replaces. Good question. No, not easily. You could do it in a roundabout way, but you'd probably be best off just overwriting several callbacks or appending several callbacks. Yeah, because they only get executed when the thread gets deleted in some scenarios. So you have the thread which stores those callbacks auto exit. All right, thank you very much. Cheers.